China says it's building a train that moves at 1,000 kilometers per hour. That's faster than most commercial jets. The internet is buzzing about 2026. But here's what nobody's asking. What will actually exist in 2026? I mean, what's physically real? Let's start with what we're actually talking about, because calling this a train is technically accurate, but completely misleading. This is a magnetic levitation vehicle, traveling through a low vacuum tube. It doesn't touch rails. It doesn't move through normal air. It operates in an environment closer to the edge of space than to a subway tunnel. When China talks about 1,000 kilometers per hour, they're describing a system that combines three separate cutting-edge technologies. First, magnetic levitation, the same tech behind Shanghai's existing Maglev that's been running since 2004. Second, linear motor propulsion, which pushes the vehicle forward without mechanical contact. Third, and this is the critical part, a partially evacuated tube that removes most of the air resistance. That last piece changes everything. A regular high-speed train at 350 kilometers per hour uses about 80% of its energy, just fighting air resistance. Remove most of that air, and suddenly you're not just going faster, you're operating in a completely different physics environment. What creates confusion is when you see headlines saying, China's 1,000 kilometers per hour train. Your brain pictures something like a bullet train, just faster. That's not what this is. This is closer to a ground-based aircraft operating in a controlled tube environment. The distinction matters because people compare this to planes and ask, why not just fly? The answer reveals why China is pursuing this in the first place. A plane at cruising altitude travels through thin air at high speed, efficient once you're up there. But getting to altitude burns massive fuel. This Maglev operates at ground level in artificially thinned air, which means you get plane-like speeds without the energy cost of climbing to 35,000 feet. But there's another comparison that matters more. Trains. China's existing high-speed rail network runs at 350 kilometers per hour commercially. That system is profitable, proven, and connects hundreds of cities. At that speed, Beijing to Shanghai takes about 5 hours. At 1,000 kilometers per hour, 90 minutes. That's not just faster, that changes what distance means. It turns a trip you plan your day around into something you do between meetings. It makes cities 1,000 kilometers apart feel like suburbs of each other. It transforms regional economies into a single integrated zone. So when China talks about this technology, they're not talking about replacing planes. They're talking about erasing the difference between near and far, what already exists today. Now, let's get specific about what's real, right now, verified, on the ground. In Yangao County, Datong City, Shanxi Province, there's a test facility. Construction started in April 2022. By November 2023, it was complete. It's a 2-kilometer low vacuum tube with a full-scale Maglev vehicle inside. In August 2024, they ran a demonstration test. The vehicle operated in low vacuum conditions, maintained stable suspension, navigated curves, and stopped safely. All systems performed as predicted, but here's what they didn't announce: the exact speed. What we know for certain is that in February 2024, this system called T-Flight hit 623 kilometers per hour during tests. By August, when they tested under low vacuum conditions, reports suggested speeds exceeded that previous record, but no specific number was released. According to industry reporting, additional test programs have demonstrated remarkable acceleration capabilities. Reports suggest facilities in Hubei province and at defense research institutions have achieved velocities above 650 kilometers per hour in controlled short-distance tests, with some reaching these speeds in under 10 seconds. These aren't the same system as the Shanxi vacuum tube facility. They're different research programs exploring different aspects of ultra-high-speed Maglev technology. Some focus on vacuum tubes, others on electromagnetic acceleration, others on superconducting systems. What this tells you is that China isn't pursuing one Maglev project. They're pursuing several, simultaneously, each testing different approaches to the same problem. How do you move people at near aircraft speeds on the ground? Now, there's also Shanghai's existing Maglev. It's been operational since 2004, carrying paying passengers every single day. It currently runs at 300 kilometers per hour. Commercially, it used to hit 431 kilometers per hour until 2021, when they reduced the speed for operational reasons. That train proves something critical. Maglev technology works in the real world. It's not theoretical. People ride it. It operates safely. The question isn't whether Maglev can work. The question is whether vacuum tube Maglev at 1,000 kilometers per hour can scale beyond test facilities. The vacuum tube component comes from CASIC, the China Aerospace Science and Industry Corporation. Yes, the aerospace division. They've built experimental tube sections and demonstrated that they can maintain low pressure, about 1/10 of normal atmospheric pressure, over meaningful distances. Engineers have shown they can get Maglev vehicles moving inside those tubes at high speeds without catastrophic failure. The physics works, the technology functions. Here's what that pressure reduction actually means. Normal atmospheric pressure at sea level is about 101 kilopascals. These vacuum tubes operate at roughly 10 kilopascals, thin enough to dramatically reduce air resistance, but not so thin that maintaining the vacuum becomes impossibly expensive. So the components exist, the tests succeed. But here's what doesn't exist: a single kilometer of operational, commercial, passenger-carrying vacuum tube Maglev track anywhere in the world. Not in China, not anywhere. What exists today is proof that the physics works. What doesn't exist yet is proof that the system works at scale, over long distances, in all conditions, day after day, with the kind of reliability that passenger transport demands. What is not ready yet? Let's talk about what's missing, because this is where reality separates from headlines. First, there's no operational route. Not a single kilometer of commercial, low-vacuum Maglev track connects any two cities. The test tracks are research facilities. They're not designed to carry passengers. They're not connected to population centers. They're built to answer engineering questions, not move people. The infrastructure problem is big. Imagine building a tube, a sealed, structurally sound, vacuum-maintained tube for 1,000 kilometers, not a tunnel. A tube that has to maintain low pressure, withstand thermal expansion, survive earthquakes, and remain airtight while a vehicle passes through at 1,000 kilometers per hour. Now imagine building that tube through mountains, across rivers, around cities, through regions with wildly different climates. The engineering challenge isn't just hard, it's unprecedented. Every connection point becomes a potential failure point. The tube has to handle temperature swings from summer to winter. It has to survive typhoons, earthquakes, and the constant stress of vehicles passing through at extreme speeds. And unlike a regular train tunnel, where a small crack just means water seepage, a breach in a vacuum tube means rapid pressure loss that could affect vehicle stability at 1,000 kilometers per hour. Then there's the safety question that nobody wants to discuss publicly, but engineers obsess over. What happens when something goes wrong inside a low vacuum tube at 1,000 kilometers per hour? You can't just open a door and walk out. You're in an environment with 1/10 normal air pressure. Rapid depressurization could be catastrophic. Emergency evacuation systems have to work in conditions where normal breathing is impossible, and every second counts. Compare this to a plane. If a plane has an emergency, it can land at thousands of airports. If this Maglev has an emergency inside a sealed tube, hundreds of kilometers from the nearest exit, what happens? The answer is, China's engineers are working on it. Pressurized emergency compartments, rapid repressurization systems, evacuation protocols, emergency access points along the route. But these systems haven't been tested at scale in real emergencies because, thankfully, there haven't been real emergencies yet. And here's the complexity nobody talks about. You can't just have emergency exits every few kilometers like a highway tunnel. Every exit point is a potential vacuum breach. Every access door has to maintain pressure integrity while still being accessible in an emergency. The engineering trade-offs are immense. Energy is another challenge. Maintaining a low vacuum environment over 1,000 kilometers requires constant power. Pumps run continuously, seals must hold. Any breach means pressure loss, and pressure loss means the system stops working. Think about the scale. 1,000 kilometers of tube, maintained at low pressure, 24 hours a day, 365 days a year. The energy requirements aren't just for moving the train, they're for maintaining the operating environment itself. Cost is almost impossible to calculate, because nothing like this has been built before. Industry estimates suggest China's conventional high-speed rail runs about $17 to $21 million per kilometer. Previous Maglev projects, like Shanghai's system built with German technology, came in around $40 million per kilometer. For vacuum tube Maglev, preliminary engineering assessments suggest the tube infrastructure alone could add another $25 to $30 million per kilometer on top of conventional Maglev costs. That would put total construction costs in the range of $65 to $70 million per kilometer, potentially higher depending on terrain and engineering complexity. Using these estimates, a 1,000 kilometer route could cost $65 to $70 billion, possibly more. For context, That's roughly the entire GDP of Sri Lanka. That's more than the annual military budget of Germany. That's the range you get when you talk to engineers who understand the technology and the construction challenges. And here's the reality check. That money doesn't guarantee success. It guarantees an attempt. Maintenance is another unknown. How do you repair a vacuum tube while maintaining service? How often do seals need replacement? What happens when the tube needs inspection? With conventional rail, you can do maintenance at night and run trains during the day. With a vacuum system, any maintenance that requires opening the tube means depressurizing sections, which takes time and energy. So when you ask what's not ready for 2026, the answer is almost everything required for commercial passenger service. The technology works in controlled conditions. Scaling it to real-world operations over long distances with paying passengers is an entirely different challenge. Why China is still pushing this? So if it's this hard, this expensive, this uncertain, why is China doing it? The answer has almost nothing to do with trains, and everything to do with what trains represent. Start with the long game. China's leadership thinks in decades, not election cycles. They're not asking, can we launch this in 2026? They're asking, who controls ground transportation technology in 2050? Right now, China already dominates high-speed rail. As of the end of 2025, they have over 50,400 kilometers of high-speed track. That's more than the rest of the world combined. They build it faster, cheaper, and at larger scale than anyone else. They export that technology to dozens of countries. When Indonesia or Thailand or Saudi Arabia wants high-speed rail, they call China. That's influence. The Jakarta-Bandung high-speed railway in Indonesia, opened in 2023, is a perfect example. Built with Chinese technology and financing, it's now carried over 13 million passengers. That's Chinese engineering solving Indonesian transportation problems, creating a relationship that goes far beyond a simple sale. If China develops low-vacuum maglev and makes it work, even if it takes until 2035 or 2040, they own the next generation of ground transport. They set the standards, they export the systems, they become the default partner for any country that wants cutting-edge infrastructure. Think about what that means geopolitically. When you build another country's critical infrastructure, you're not just selling equipment, you're creating dependency. You're embedding yourself in their economy. You're making it very expensive for them to switch to someone else. There's also the aviation angle. China's domestic aviation market is enormous. Moving 1.4 billion people generates massive air traffic. Air travel is expensive, energy-intensive, and constrained by airport capacity. If you can move people at near aircraft speeds on the ground, you reduce pressure on airports, cut fuel consumption, and gain more control over your domestic transportation network. You're less dependent on imported aviation fuel. You're less vulnerable to airspace disruptions. And here's the part that matters for China's leadership. You keep people on the ground, where control is easier. Airports are complex security environments. They're vulnerable to disruption. They require massive land near cities. They create noise pollution that generates public opposition. Ground transportation, by contrast, offers more control points, more flexibility in routing, and fewer constraints on where you can build. Then there's technological signaling. Every time China announces progress on this project, it sends a message to the world. We are the country pushing technological boundaries. We are the ones building the future. That message matters economically. It attracts investment, talent, and partnerships. It positions China as the leader in next-generation infrastructure, which makes other countries more likely to engage with Chinese companies and adopt Chinese standards. But there's a deeper strategic calculation. China's economic model depends on continuous technological advancement. The easy gains from cheap labor and export manufacturing are over. The next phase requires moving up the value chain, becoming the place where advanced technology is developed, not just manufactured. Low-vacuum maglev is a demonstration project for that transition. It shows domestic and international audiences that China can tackle problems nobody else is solving. It proves that Chinese engineering can work at the cutting edge. And even if the full vision takes decades to realize, the research itself generates value. The vacuum technology has applications in semiconductor manufacturing. The materials science advances help aerospace programs. The control systems improve automation across industries. The spillover effects justify the investment even if the train never carries a single paying passenger. Consider this. Hyperloop One, the American company that tried to build similar technology, shut down in 2023 after burning through $450 million. Virgin Hyperloop conducted passenger tests but never achieved commercial viability. European efforts stalled. China is now the only country still seriously pursuing this technology at scale. That alone tells you something about China's approach to infrastructure. They're willing to absorb the risk, invest over decades, and accept that failure is possible because the potential payoff is so large. So when you ask why China is pushing this, the answer is because the benefits of trying outweigh the costs of not trying. This isn't about 2026, it's about 2050, and who shapes the world between now and then, what 2026 actually represents. Let's be absolutely clear about something. China has made no official announcement targeting 2026 as a milestone year for this technology. No government statement, no CASIC press release, no timeline from official sources saying 2026 is the year. So where does 2026 come from? Speculation, extrapolation, people looking at the pace of development and guessing. Here's what 2026 actually represents: a checkpoint. By the end of 2026, we'll be able to see whether this technology is moving from laboratory experiments to repeatable, scalable systems. We'll see whether test speeds continue increasing. We'll see whether longer test sections get built. We'll see whether the engineering challenges are getting solved or just getting more complex. Think of 2026 as the year that separates interesting research project from this might actually happen. There's also a separate Maglev project that matters here. In July 2025, CRRC, China's state-owned rail manufacturer, unveiled a 600 km/h Maglev train. Not 1,000, 600. And this one doesn't use vacuum tubes. It's conventional Maglev, proven technology, just faster than anything currently in commercial service. That train is expected to enter commercial operation within 5 to 10 years. That means 2030 to 2035. If that timeline holds, 2026 becomes the midpoint between unveiling and operation, the year when we see whether construction on actual commercial routes begins, whether cities commit funding, whether the technology moves from unveiled at a conference to breaking ground on track. But the 1,000 km/h vacuum tube system, that's on a different, longer timeline. What might actually happen in 2026? Probably longer test runs, higher sustained speeds over greater distances, better vacuum management systems that can handle longer tube sections, improved safety systems with real-world validation. These aren't sexy headlines, but they're the foundations that make commercial operation possible later. There's also the possibility of a longer test track being announced or constructed. The current 2-kilometer facility proves the concept. A 20-kilometer or 50-kilometer test section would prove operational viability, showing that the system can handle longer distances, sustained speeds, and the thermal and structural challenges of extended operation. Don't expect a ribbon-cutting ceremony with passengers boarding a 1,000 km/h train. Expect progress reports, test results, engineering validation, proof that the concept can scale. And watch for announcements about which route might be first. Beijing to Shanghai is the obvious candidate. 1,200 kilometers, massive passenger demand, existing high-speed rail for comparison. But the cost and complexity might push them toward a shorter initial route to prove the technology before committing to something that large. 2026 is year one of the operational development phase, not the delivery date. Here's the thing about this project that most people miss. China doesn't need this train to work tomorrow. They don't even need it to work in 2030. They only need it to work eventually. Because once it works, once they demonstrate that you can move people 1,000 kilometers in an hour, safely, reliably, at reasonable cost, the world changes. Cities that are too far apart to integrate become one economic region. Populations that are isolated by distance become connected. Countries that can't afford the technology become customers. And the country that builds it first writes the rules for everyone who comes after. So when people ask what's actually ready for 2026, they're asking the wrong question. The right question is, when China eventually makes this work, and based on everything they've already built, eventually seems likely who else will be able to compete. Look at what they've already done. In 2008, China had 672 kilometers of high-speed rail. By 2025, they have over 50,400 kilometers. That's 75 times more in 17 years. They went from importing technology to exporting it, from student to teacher. 2026 won't bring the 1,000 km/h train to your city, but it will show whether that train is coming eventually. And eventually, in infrastructure, is what matters. Let us know your thoughts in the comment section. High-speed trains are only one piece of the puzzle. China is also reshaping global aviation itself. That story starts here. Click to watch that video next.